Hello, my name is Panagiotis Sidiropoulos and I'm a postdoctoral researcher in the imaging group of MSSL UCL, and I'm going to talk to you about automatic detection of Mars surface changes using high-resolution core-register images. Now the first slide is about, it shows us a map of high-resolution images that have been acquired from Mars surface, from orbit. And in this coverage map, the red pixels correspond to areas that have been mapped extensively, at least 20 times, while the blue regions correspond to areas that have been sparsely mapped, once or twice. What you can see in this map is that there are large regions that have been extensively mapped, for example the poles, or Valles Marineris or Limbus Mons regions that are regions of interest, and also some of the red spots correspond to landing sites of rovers that have been also extensively mapped. But the general picture is that we have a large area of Mars that has been mapped repeatedly using high resolution images. And because we have this abundant imagery, this means that we can conduct a batch mode change detection. The problem with the traditional way to detect changes is that this is done manually, this is done by humans, and because the regions that have been mapped more than once are so large, the regions are so extensive, we don't have enough eyes to look for the changes. So instead of using humans to detect changes, we have developed an automatic technique that can do the same thing faster and without using any human resources. So the input of the algorithm that we have developed is a pair of images that have been already co-registered using our co-registration pipeline, and also we are using the corresponding DTM. And in the algorithm, the first thing that we do is to find pixel level changes, which mean pixels that have inconsistent gray values, and in the second step we discard the isolated pixel level changes, because it is very difficult to determine if these actually correspond to changes or if they are just noisy entries in the data. So we discard these and aggregate the rest of the changed pixels into blobs, into sets of changed regions. And in the third step, we discard the changes that are caused by illumination effects, for example, shadows, because an area that has been mapped using different illumination conditions can seem like there is a change in there while not being one. It's just having different shadows. So we discard these changes in the third step of the algorithm, and the remaining candidate changes are the input of two-layer classification module, supervised learning module. In the first layer, we have 4 different modules, and each one focuses on a certain type of changes, and the output of this layer is combined, is merged in a second layer classifier, which actually gives us the final output, the changes that are found. And the output are regions of interest which are determined by the change detection, but they don't only include the change. We use a constant size of 512 to 512 in order to give also some context about the change. And the resolution is equal to the resolution of the coarsest image, so that can be comparable to each other. And also we save some metadata like the latitude, longitude of the change, the pixel coordinates, of course, the dates of the before and after image, and of course the names, the actual images. So we have used this algorithm extensively in the co-registered images that we have already, and we are continuing. This is an ongoing process. While we co-register images, then we pass the processing to the change detection pipeline. And the most common changes that we have found is the dust devils. There are hundreds of dust devil tracks on Mars, and this is something that's already known in the literature, that dust devil tracks is the most common type of surface change. You can see here an image. This is the before image, and this is the after image. You can see that there was some dust devil tracks in the first image that were erased in the second one. Not only we detect dust devil tracks, but we have also detected the actual dust devils in action. We have found more than 10 dust devils, and here in this slide you can see 5 of them. Apart from dust devils, we have also detected clouds, and one of the most interesting things that we have achieved is to detect new impact craters. In the top row you can see 2 images, the before and the after image. The left panel is the before and the right one is the after, and you can see that we have detected a new crater. But this crater was already reported in the literature. In the bottom row, however, we have detected an impact crater that is new. It's not reported in the literature. This is in MC11 East, and we have found 4 changes that are 4 images that are involved in this change. So the first, the left panel is from Themis Vis. It's a 2005 image, and it is the last image before the impact. The second one is the CTX image. It's the first image after the impact. You can see the characteristic dark blob in the area that impact happened. While the third image is a Themis image from 2008, and in this case the blob has separated into 3 smaller blobs that correspond to the 3 impacts that happened, because actually the meteorite split into 3 particles before the impact. And in the fourth and last image, which is from 2014, the surface appearance has been reinstalled as was initially, with the only difference that we have 3 new impact craters in the place that the impact happened. So this is a new crater, and we hope to find much more than just one in the future. But apart from that, we have already found slope streaks in areas that are already reported in the literature, and we have also found a lot of changes happening in areas of slopes, and we are going to examine them more thoroughly and hope to find more slope streaks, but also changes related to active gullies or RSLs. So this is a work that is happening. It will happen in the near future, but also we are going to process the whole planet. We are going to do change detection in all the co-register images that we are going to get, and we plan to detect much more changes, much more new instances, and augment the catalogs that are already in the literature.